Hello everyone, today let's take a look at Quantipus number 50, which is a circular permutations type of problem. Basically, you're hosting a dinner party for 8 guests around a circular table. So in part A, how many different ways can the guests be seated relative to each other? And in part B, if two particular guests refuse to sit next to each other, how many valid seating arrangements remain? So I drew out a little table here where every single one of these is a seat, and let's look at part A first. The first way I can think about it is, okay, I have 8 guests. I can place guest 1 in any of the 8 available chairs, and then once I've placed guest 1, I can place guest 2 in any of the 7 remaining available chairs, and then etc. So we're just going to wind up with 8 factorial, but then it's a circular table, and we're interested in how the guests can be seated relative to each other. So for instance, this orientation right here is basically the exact same as this one here. If we just rotated everyone once, and then it's going to be the same as this one and this one too. It's kind of hard to do this rotating thing, but you can see that these are all going to be the same. So essentially for every single one of these 8 factorial permutations, we could just rotate everyone over this way. How many times can we do that? Well, we could do that 8 different ways because there's 8 seats, so we have to divide by 8. Obviously 8 factorial on 8 is just going to be equal to 7 factorial, so that's one way to think about it. Another way to think about it is just imagining if I just fixed one guest to their chair, well, then there would be 7 factorial ways to permute the 7 remaining guests. And more generally, when you're seating n guests around a circular table, there's going to be n minus 1 factorial ways of permuting them relative to each other. So this is the answer for part A. Let's go on to part B now. So in part B, let's just assume that guests 1 and 2 don't want to sit next to each other. So how many permutations are there where they do not sit next to each other? So to do that, we can just take the total number of permutations, 7 factorial, and subtract off the cases where 1 and 2 are next to each other. So let's force 1 and 2 to sit next to each other, basically by creating this little blob here. So now essentially we have 7 elements around this table. We need to calculate the number of permutations. Well, again, we could just say 1 and 2 are fixed in place, and then we're going to have 6 factorial ways of permuting the rest of the guests. So we're going to have 6 factorial, but wait a minute, we're not done. So let's just expand this little blob here. In the blob, we have 2 elements, so there's going to be 2 factorial equals 2 ways of permuting them, right? We could either have 1 and then 2, or we could have 2 and then 1. And for each one of these cases, we have 6 factorial permutations of the other guest, right? So we need to multiply this by 2. So these are the permutations where 1 and 2 are next to each other. So let's take 7 factorial and subtract off 6 factorial times 2 to get our final answer. And this is going to give us the number of permutations where 1 and 2 are not next to each other. And it's going to end up being 3,600 once you work this all out.